Okay, so here's question 14, and what we're being asked to do here is work out the mass of radium-226 needed to give an activity of 5 microcuries. Now, curies is a unit of activity. It's not the one that we usually use, but we're told what the conversion factor is here. We know that 1 curie is equal to 3.7 times 10 to the 10 becquerels. So as a result of that, we can work out our original activity here, because we know that we've got a source of 5 microcuries, so 5 times 10 to the minus 6 curies, and we're just going to multiply that by 3.7 times 10 to the 10, because 1 curie is that number of becquerels, and that will give us 1.85 times 10 to the 5 becquerels. That's the original activity of our source in becquerels. Now, what other information do we know here? Well, we know the half-life is 1,600 years. Okay, so now what we're asked to do is work out the mass of radium-226 needed to give this activity. Okay, so we now need to work out the number of atoms that are present, and the way to do that is use the equation A equals lambda n. So n naught is going to be equal to A naught over lambda. Okay, now we already know what A naught is. It's 1.85 times 10 to the 5 becquerels. Now lambda is just equal to ln2 over t half. Okay, that's lambda, so it's going to be ln2 over the half-life. Now the thing is here, because this is in becquerels, we need to get this in per second. So if this is the number of years here for the half-life, we need to convert the half-life into seconds. So to do that, we multiply by 365 times 24 times 60 times 60. Okay, and then we can work out our decay constant. So ln2 divided by 1,600 years, but to convert that into seconds, multiply by 365 days, 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. Okay, and that gives us then our decay constant in the unit per second rather than per year. So we can then put that into here and work out the answer. So 1.85 to 5 divided by 1.37 minus 11 gives us 1.35 times 10 to the 16 atoms. Okay. Now, we now need to work out the mass of radium required. Now, in order to do this, you need to know basically that this here, this number here, is the relative atomic mass, okay, or the molar mass, but also it tells us the mass of one atom is equal to 226 unified atomic mass units. Okay, now you can find in your data booklet that a unified atomic mass unit is equal to 1.66 times 10 to the minus 27 kilograms. Okay, which is basically the mass of a hydrogen. Basically the mass of a proton. Now, what we can do then is this: if we know that one atom is 226 U. Okay, then we know that one radium atom must be 226 times by 1.66 times 10 to the minus 27 kilograms, which gives you 3.75 times 10 to the minus 25 kilograms. Okay, so that's the mass of one atom in kilograms, but we're asked the mass of radium required. Now we know the mass of one atom, and we know the number of radium atoms required to give us this activity. So all we need to do now to work out the total mass is to multiply these two things together. So the mass of one atom multiplied by the number of atoms. Oops. And that's going to give us an answer of 5.06, whoops, 0.06 times 10 to the minus 9. Now that's in kilograms, so to get that into grams you multiply by 1,000, which gives you that, and that's equal to 5.06 micrograms. Okay, so there you go, that's that answer done. Now there is an alternative way of doing this, which is absolutely fine if you want to do it. It doesn't matter which way you do it. Okay, and the alternative method is as follows. Now we know from previously that the number of nuclei that we need, or the number of atoms that we need, is 1.35 times 10 to the 16. We know Avogadro's number is the number of atoms in a mole, so you should know that from chemistry, and we know that the decay constant is 1.37 times 10 to the minus 11 per second. We worked that out earlier. So if you want to do this in a different way, you can use some of the equations you know from chemistry. Okay, so the number of moles is equal to, whoops, that should be a capital M, is equal to lowercase m divided by capital M, where the lowercase m is the mass of substance in grams and the capital M is the molar mass or the relative molecular mass. Okay. Also, we know that the number of atoms is equal to the number of moles multiplied by Avogadro's number, because Avogadro's number is the number of atoms in a mole. So what we can do first of all here is work out the number of moles by doing the number of atoms that we've got divided by Avogadro's number. So we know that we've got 1.35 times 10 to the 16 atoms. I'm going to divide that by 6.02 times 10 to the 23. Okay, so that's going to be 1.35 times 10 to the 16 divided by 6.02 times 10 to the 23. That's going to give us 2.24 times 10 to the minus 8 moles. Okay. Now that we've got the number of moles, you can then use this equation to work out the mass of substance in grams. The mass of substance M is equal to the number of moles multiplied by the relative molecular mass or the molar mass. So 2.24 times 10 to the minus 8, and then the molar mass or relative molecular mass is 226 grams per mole. So when you work that out, you're going to get 2.24 times 10 to the minus 8 times 226. Whoops. Again, it doesn't matter if you use the rounded value or the full value off your calculator. But what you do notice is it will give you a slightly different answer. So in this case, we've come out with 5.07 times 10 to the minus 6. And remember, that's in grams because this is in grams per mole if it's the molar mass. Okay, sometimes your chemistry teacher will tell you that that's the relative molecular mass and it doesn't have a unit, but there we go. So you can see slight difference from the original answer here, but again, that's just due to rounding issues, and that's fine. As long as you show your work in, there's no problem with that. You'd get the answer, the full marks in the exam either way round. Okay, so there you go. Now let's do part B. Okay, so part B here, we're just going to use this equation. A equals A naught e to the minus lambda t. And what it's asking is what fraction of the original activity would be left after 50 years? Now the fraction of the original activity is given by A over A naught. And that's obviously equal to minus lambda t, e to the minus lambda t. Now we know that this here, we already know the decay constant, but remember that's in per second, so you've got to be careful here. We're going to multiply this by the time, which is 50, but because it's years, we've got to change that into seconds because this is per second. So we're going to multiply by 365 times 24 times 60 times 60. Okay, and that's going to give us our answer. So let's type in the numbers. Minus 1.37 times 10 to the minus 11. Multiplied by 50 times 365 times 24 times 60 times 60. And there you go, that's going to give you 0.979. And you should hopefully be able to work out that that is, if you round that up, that's going to be 0.98. So it's 98%. Okay, so 98% of the radium-226 remains after 50 years, which makes sense because the half-life is 1,600 years. This is significantly less than that. And there we go, that's question 14 done.